Okay, hello everyone. In the last lecture, I showed you a problem of a projectile where we launched the tennis ball in 45 degrees. I don't speak Welsh, if that was Welsh. So we had a 45 degrees where we launched the tennis ball. Then I asked you what happens if we had 30 degrees compared to, so this is a 30 degrees. And in red, we have a 60 degrees. So the ball would go from point O, and it would arrive at some point S. And we said, we know because of the, it doesn't matter if it's 30 or 60 degrees, it would have to reach that point as well if it's with 60 degrees. But obviously the path that it makes is different. And my question to you was, which one would arrive earlier? Or maybe they would arrive at the same time. I hope you thought about this already and that you came to the conclusion that they cannot get to point S at the same time. Not only that, but also that the 30 degrees would arrive at a shorter time. All you need to do in order to understand this is decompose this vector. Now, the magnitude of this vector is the same, that's true. And if we decompose it, then we find out that in the case of 30 degrees, the vector in the x direction is longer than the vector of the x direction in the case of the 60 degrees. I'll put it here. Now, think about it like this: both of the in the two cases, they will have to go from left to right. Now we're talking in the x direction, so it's the same. It's the same distance, right? It's OS. It's the same distance. But this vector here has a magnitude which is larger than that vector. And this is the same distance, so it has to be reached at shorter time. So this is one thing that we should understand from this exercise. There's another very important point that would actually lead us to the subject of this lecture. And that is, you note that when we decompose the vector, and I hope you start seeing the benefits of this. When we solve in the x direction, in this specific case, you see that the vector, the velocity vector, is constant all the time. It doesn't change. If you write down the equations of motion in the x direction, you will see that it's just x equals some x0, right, which you can take as 0, times vt, and v here is the velocity in the x direction. So it's constant. And the reason that that vector is constant, is not changing, is there is no acceleration acting upon the object in that direction. But you see that in the y direction, it actually changes direction, right? So it starts going up. After some time, it stops completely at this point, and then it starts going down. So it changed direction. So this is an important conclusion that we have to make as well, is that if you have a velocity vector, if the object is traveling with some velocity vector, we would expect it to keep traveling in that velocity, in that direction. It won't change the direction unless if there is some kind of acceleration acting upon it. Now we want to analyze this idea, and to do it, we do it in the simplest possible way initially, and that is by considering such a motion. So we have a circular motion, a uniform circular motion. Okay, this is the motion that we're going to discuss. We have this object, and this object is traveling in a circular motion, not only circular but uniform. We're going to see what uniform means shortly. Before I start with the lecture, I wrote here for the reading. Please do complete the reading up to and complete and including the fourth chapter. This would cover all the material that you had so far, including the material that you would have also next week. We're going to discuss, start discussing Newton's law. So you might have, you will have some new materials in the chapter 3 and 4, but you can prepare that for the next lectures as well. Okay, so the problem that we have is the following. We have an object, and as always, what we want to do with that object is we want to predict the motion of that object. That's why we analyze the problem. So we have an object, and that object, let's say it's here at some time, and it's going around in a circular motion. To keep things simple, there is no gravity, okay, no gravity. For the moment, there is no gravity. We know the radius of this circular motion, which is given by r, and I can put a position vector from the origin pointing at the object, and that position vector would follow the object everywhere it goes. Okay, so this would be my position vector. This is my RT. This is my position vector, and it's a function of time. Just as we did with the projectiles, it's the same idea now. This is a circular motion. This is the only difference. What do we know? We know that there's a velocity v, which is tangential to the object, to the circle at this point. So the velocity vector is v, and the direction is tangential. It can't have any radial components, and the reason is if there is a radial component, then you would start seeing it doing something which is different than the circle. This is a circle, so the motion is, the velocity vector is always tangential to this circle. So at some point here, it would look like this, and at some point here, it would look like this. What is also given, and I said uniform motion, which means the magnitude of this velocity vector, or the speed, if you want, of the object at any point is the same. So the magnitude of the velocity is not changing, but obviously you see that this vector is, at this point is pointing there, at that point is pointing there, and at any moment in time is actually changing its direction. There was a question which I couldn't read. Let me see if I can see the chat. What is drawn in red is the position vector. Okay. Yes. Oh, okay. Yeah, Berna, you're there. That's great. So I can carry on while you answer these questions. Okay. So this is the position vector, and it points at that everywhere it goes. So it makes this circular motion. That's the position vector. the magnitude of this vector is obviously the same, right? This is the radius, it's the magnitude of the vector, but the direction is changing. It makes this radial motion. Okay, so what do we conclude here? The first thing we should conclude is because the velocity is changing, right? The velocity vector is changing, there is some acceleration acting on this object. That is the first thing that we should conclude. Now, to make things maybe easier, you can think of this problem here, right? And forget about gravity. I can do it also in other planes. Forget about gravity. So the acceleration does not come from gravity right now. And you have this motion. The vector, the position vector is actually this, right? This is the position vector. It comes from the origin and it points on the object. Now this is a string. Now I would expect that the acceleration would be somewhere in the direction of this position vector, the string. We're going to derive this shortly. Before that, I'm going to make some definitions that are going to be useful for the rest of the lecture. Because this is a uniform motion, as the object makes one complete cycle, which means from any position that you choose, let's say from here, it goes around one time, that would be the period, okay? So t is the period. It's the time that takes the object to go around one time. And this is measured in seconds. I can also describe the motion in a different way, how many times it rotates per second. So I can take a timer and check in a second how many times this object actually rotates around. And that would be the frequency. So the frequency is 1 over the period, and that is 1 over second in terms of the units. Right, I'm going to write here, this is the frequency. And this is known as hertz. So hertz is 1 over second. How many rotations per second do we have? So this is also how the number, this is for the number of rotations, so rotations per second. Okay. So the frequency is 1 over the period. Now, because we talk about the circular motion, it's more convenient to talk in terms of angular movement. So instead of this velocity, we can define the angular velocity. That would be omega. This is omega now, and this is the angular velocity. And the angular velocity would be not how many meters per second as we had before, but it's in radians now. Okay, so that's why you'd have 2 pi. So you'd have 2 pi over t. Now this is true for this case, which is also the angular frequency. And this is a sensitive point where in the future it might confuse you because we use angular frequency and angular velocity. We use the same symbol, but they are two different things. In circular motion, in uniform circular motion, numerically they are the same for some reasons that we would look into. So this is another definition. It's just a definition now that we have. And immediately you see that if you talk about angular frequency, we will talk about that later. So just to note that angular frequency would be 2 pi f. Okay, but this is now angular velocity in uniform motion, because you have a 2 pi, right? You have a 2 pi in one circle. Okay, let's get into the analysis. We have this circular motion. The velocity vector here, v, which is a function of time. I take this being the x-axis, and this is being the y-axis. We know this is the position vector, right? R. Sometimes I put the e down here, or here's the same thing. You'll have to get used to the different ways of noting the same thing as well. And the best way of doing this is by understanding the physical meaning of each component in the equation. So this is the position vector, and it's a function of time. The first thing we do is we decompose this vector. Now let's assume that at this specific time we have theta here. So theta has to be a function of time. In the x direction, we will have r cosine theta, and in the y direction, we will have r sine theta. What is the magnitude of the position? I already said that the position vector, the magnitude is simply r. It's the radius. The radius is not changing. So I can write r t, I decomposed it, right? R cosine theta in the x direction plus r sine theta in the y direction. And it's rotating at a constant speed, omega. So omega is the angular velocity, and that is how the angle is changing in time. So d theta dt. We're going to make use of that, but this is constant. That's important. This is the definition of uniform motion. The circular uniform motion. Does it have to be like that? We start with this case. Okay, we want to find the acceleration in the system, right? Remember the objective. Why are we doing this? We want to find the acceleration. To find the acceleration, if I know the position vector of this object, all I need to do is differentiate twice with respect to time, and I will be able to find the acceleration. So let's do this. I'll do it in steps now. So v, start with the v of t. V of t is dr dt, right? The position vector. I take the derivative with respect to time, and that is, you can see here, it's easy to see that. So you have r times minus sine theta yeah, r times minus sine theta. Something is missing. Oh, yes, yes. You have to remember that theta is a function of time. Now, because theta is a function of time, we have to take the derivative also of theta. So that is d theta dt. I'll write it here now. So d theta dt, but this is giving as omega. We're going to replace it by omega later on. And this is in the x direction. I do the same thing in the y direction plus. So we have r cosine theta times, I'm going to write now omega, right? Because it's d theta dt. And this is in the y direction. I'm still inside? Yes, okay. What we do next, maybe before we do that, let's make some order here, and then we have to take the second derivative. Okay, let's take some order. We can take minus omega r outside. If I take minus omega r, then I end up with sine theta in the x direction, and then minus cosine theta in the y direction. Okay, this is from here. That's all, right? Now we can take the second derivative. So a is dv dt minus omega r times. This gives a cosine theta in the x direction. Don't forget the d theta dt. That would give 1 omega. Let's keep that in mind. And this minus here would give us plus sine theta in the y direction. There's another omega here. So 1 omega here and 1 omega there. We're going to have omega squared. I put it outside. Great. Now what is this? Well, we're back to the position vector. If you multiply by this r, this is the position vector. So the acceleration in the system equals minus omega squared, the position vector. Write it here. So A of t equals minus omega squared, a position vector, which means the magnitude, if I'm just interested in the magnitude for now, is simply omega squared times r. Now, we want to read physics. We don't want just to look at the equations we derive. And what this tells me is that the magnitude of the acceleration is proportional to the radius of the circular motion, the uniform circular motion. The larger r becomes, the larger the acceleration becomes. If I make r twice as large, giving the same omega, the acceleration would be twice as large. We call this acceleration, normally we denote it with c. I'll write it down soon. Okay, so denote it with c. This is known as the centripetal acceleration. Okay, centripetal acceleration. It's just a name. Okay. Now let's go back to the velocity, the speed, actually. So the speed I can write as this is better. So v is 2 pi. Remember, 2 pi over t gives the angular velocity, and if I multiply it by r, this is omega r. I can write it here. So this is the speed. Okay. This is the magnitude, okay? It's not a vector. So the speed is not changing. The speed is constant. You define omega, you keep r constant, you see that the speed is constant. But the vector, the velocity vector is changing in every moment. So there must be an acceleration, as we said. An example here. I will keep I want to show you some demonstrations, so I'll keep the examples for Berna after the lecture. But as I said, what I want to emphasize is that A is proportional to the radius. So if I take this same object, given that I'm able to give it the same angular velocity, but now if I make it longer, twice as long, then this object should have should feel an acceleration which is twice as large. Now, how do I know if this is the same velocity or not? It should complete one cycle in the same time. So it's also the same frequency in this case, in the uniform circular motion. In fact, if you try it at home, you would feel that as you start increasing now I'm increasing omega. As I'm increasing omega, I don't want to increase it too much, but as I'm increasing omega, I can feel that now, what do I feel is something we're going to talk about at the end of this day. It's not the acceleration, but it's something else. I feel some kind of a pull that this wants to leave. And the faster I rotate, the larger omega becomes, the more I feel of that, well, the more pull I feel in my fingers. Now imagine that you're actually rotating that object. So the object is rotating. By the way, there doesn't need to be any string, right? So you can take also the Earth and the Moon, and the Moon is rotating around about the Earth. So you can conclude that if this is a circular motion, right, and the Moon is changing this vector at every moment in time, there should be an acceleration. So there should be a centripetal acceleration, which is towards the Earth. Now, what happens if you somehow cut out that acceleration? Maybe it's easier now to picture it actually with the string. So you have the string and it's rotating, and at some moment, let's say at this moment, you just cut this string, and there's nothing that actually can allow that pull in the string that would give this acceleration to the object. Now you might think, I don't think you would, but you might think that it would go in this way, in a spiral way, away from the object. But this cannot be true, and I hope now you see this. Why? If it's making this kind of spiral motion, it means that this vector, the velocity vector, is changing direction. If it's changing direction, it means that there is still some acceleration, centripetal acceleration acting upon it. If there is no centripetal acceleration acting upon it when it's at this point, then you would say it would have to go forever in that direction. If it was here at this point, it would go straight downwards. I don't have much space here to actually demonstrate this for you. I'll keep this demonstration at the end, but if I just can try it now, if I just rotate this like this, and at some moment in time, let's see what I'm gonna break. I never like this light. I'm gonna break this light here. Okay, so I'm gonna try and leave it when it's exactly vertical. It's very hard to do that really, but if you're very quick to see, you will see it just going up, right? Let's see. So it won't make some kind of spiral motion. If I do it a little bit with an angle, what would happen then? We've solved that with the last lecture, right? So if I do it like this, I leave it when it's exactly at some point here, right? So the velocity vector in that direction, this is the problem that we solved with the project task, right? So it would have to do something like this. Now, why does it do something like this? Because there is gravity here. There is acceleration in that direction. So it would do that. So don't be disappointed if it doesn't carry on straight. Actually, I would be very surprised if I do it with a little angle and it carries up completely straight. All right, let me do it like this. So you might have a little bit more to see, which I thought you would hear more than seeing. 3, 2, 1, go. Okay. All right. That was too successful. It just went almost straight, and you could hear the sound on the ceiling. So that is the proof, at least, that it went almost straight. Okay, let's carry on. I'll show you more demonstrations at the end of the lecture. If you can have more space, I will move the camera backwards. What I want to do next is, in fact, there's one thing that I have a photo here I can show you. This is from the David and Goliath, right? And what you see is holding in the David is the smaller one, is holding in his hand a sling, which acts on this very simple principle that we discussed here. So you rotate it. The faster you rotate it, can we see this? We want to read. The faster you rotate it, the more acceleration you have. The more acceleration, it means the more impact you have, right? So you make R very long. I have another one from modern days. Actually, you see R is quite long. This is from modern days. You see this is, how long is this? And there's a stone here. The longer it is, the more acceleration you have. If you make it rotate twice as much, the acceleration would go 4 times, right? Because omega is to the power 2 here. I have an office-made sling here. I'll show you the demonstration at the end. This is a very short one, so it won't be useful actually, but I'll show you the demonstration at the end. Okay, the last thing I want to do today is to discuss this feeling of a pull whenever I rotate this tennis ball. Okay, I'm rotating this, I'm rotating faster, and I feel this pull in the string. Now, we want to include gravity in the next analysis. So I'm standing here in this room. So gravity is considered now. And I'm actually this tennis ball. Okay, so I am holding the string with my hands and just hanging from the string. And so this is me. And this is the floor. And I'm hanging from this string, just hanging. You can do it yourself also, and then I can ask you, what do you feel in your hands? You can make a mind experiment. What do you feel in your hand? You know that gravity is acting downwards, right? So gravity is downwards. But what do you feel in your hand, in the string? You would feel a pull, right? You're pulling on the string and the string is pulling back on you. So in this case, you would feel a pull from the string. And I know that gravity is in the opposite direction. So I'm standing there, I feel a pull in the string, the pull is upwards, and the gravity is downwards. Okay. Next. Now imagine that you're just standing here, and I ask you, where's gravity? And you say, well, gravity is in the, it's always in that direction, right? It's downwards. I ask you, where do you feel gravity? You say, I also feel it downwards. And then I ask you about the floor. Do you feel a pull or a push in the floor? Say, well, I feel a push now. And this is, right now, I'm standing here and I feel a push from the floor. Now, I go back to this example. So I'm holding, this is me, and I'm holding the string in there. And now we do something like this. Okay, so it's rotating while I'm holding it. So the third case would be that I'm holding it here. And it's rotating in this uniform motion. And then you ask me, what do you feel? A pull or a push? And I say a pull. But the direction of the pull is in this direction now. And you ask me, where do you feel gravity? I say, I feel gravity in exactly the opposite direction of the pull. So it's no longer the gravity that I feel, is no longer this gravity that we feel here. I feel it in the opposite direction. So this is how we perceive gravity. Okay, let's make some use of the equations that we have. Okay, we go to the outer space. There's a space station. Actually, there's an idea of a space station that you can look in a search engine. And the idea is that we have this kind of ring, and that ring is rotating at some omega. Do we need anything here? No. First, assume that you're just in the outer space. You feel gravity? No. In the outer space, there is absolutely no gravity. In the space station, This is the space station. This is quite realistic. So it can look something like this, almost like a donut. And you're just in that space station. The radius here can be, I don't know, 100 meters. So this is R, 100 meters. It's not something impossible. And now we say we want to be in that station for some long time. We want to perceive gravity the way we perceive it also on Earth. And the question is, at which omega should we rotate that donut or the spaceship in order to perceive gravity in the same way? Now we start rotating it with omega. Omega is constant. What is the acceleration in the center? 0. So the centripetal acceleration, I'm going to write the at least one equation here, so to help you with the, which I erased. So A equals omega squared R. If I'm at R equals 0, at the center here, the centripetal acceleration is also 0. But what if you're standing here? If you're standing here, you're exactly at this R equals 100. So A equals omega squared times 100. And if I want the centripetal acceleration to be comparable to the perceived gravity on Earth, then all I need to do is substitute A being our G, so 9.8. So this is 9.8 divided by 100. That should be this should be omega. Just to make things easier for calculating, we can just put 10 here. Which means omega squared would be 0.1, right? So omega would be 0.3 radians per second. From the other equation now for the velocity, you can calculate that, well, let's look at the period first. Make use of everything that I've showed you today, all the definitions. So the period would be 2 pi divided by omega. That is about 20 seconds. Yeah. And the velocity, or the speed, which is omega times r. So omega times r, that is 0.3 times 100, which is 10 meters per second. Why 10? 0.3 times 10 times 100, 30 meters per second. Yeah, 0.3 times 100, R is 100 meters, right? R is 100 meters. These numbers are not so bad. So the speed at any point here, at the radius of big R from the center, would be 30 meters per second. The period is about 20 seconds, so it takes 20 seconds to make one turn. And by doing this, we would get a feeling of the gravity as we perceive it here on Earth. Can we walk here now? Yes. Right? Now you can actually walk. You can't, in fact, you can't float any longer because you have this perceived gravity here, AC, which is exactly equals to G. Now, if you jump, it would take you the same, almost the same. You will see why almost. It would take you almost the same time that it would take you also here on the ground if you jump up and go down. I said almost the same because there is one big difference between the gravity that we perceive here on Earth, on the ground, and the perceived gravity on this spaceship. The difference is that 100 meters from this point here, there is no acceleration. So if you're in that point when they started this rotation, you will be floating. You won't feel any acceleration. So you can no longer actually walk to that point or float to that point as you would do if there is no rotation. You could use a ladder to go up there. You can pull yourself up. And the other fact is that the higher you go, the less acceleration, the less perceived gravity you would feel until you reach that point. If you reach that point, you want to be very careful because if you move a little bit to any direction, you would start falling and it's a free fall. Again, it's a little bit different than a free fall from 100 meters on Earth because then the acceleration would start with 10 meters per second squared. Here it would start with a very tiny acceleration, but it would start building up as you keep falling. So if you're at this point, you want to be very careful not to fall down. Okay, so now we can go back to this problem. Now we have gravity. Now we can add gravity to the problem that we solved. And I want to ask you about one point. So I'm rotating this tennis ball in a uniform way, but there is gravity now. Not ignoring gravity. So it's actually the actual problem that I had here before, because I could not really do anything with gravity when I told you, let's assume there is no gravity. So now this is the actual problem. This is almost a uniform, circular uniform motion, and gravity exists. And the question is, in fact, you should try it at home. You would feel that, let me try and make a smaller angular velocities. If the angular velocity is not large enough, what would happen? This would happen, right? It won't actually make the rotation. But now imagine that we do it in a way that when the object is exactly vertical, right? So the velocity vector is there. And gravity is acting on this object all the time. And you put one more position just to make things more clear. So when it's here, for example, gravity is acting downwards. It's always downwards. But the centripetal acceleration, it's always perpendicular to the velocity vector. So this is centripetal acceleration. If I put it in green now, it would be, this is AC. And what this object would feel is some combination of the gravity and this centripetal acceleration. In other words, if this is a uniform motion, the centripetal acceleration would be changing in time. The magnitude of the centripetal acceleration would be changing in time. Why? Now let's look at the extreme. Let's look at this point where the centripetal acceleration here in this direction is exactly equal to the gravity in terms of the magnitude. If the centripetal acceleration is exactly equal to the gravity in terms of the magnitude, it means to have this object actually make that circular motion, I don't need to apply any centripetal, any pull, really, right? There would be no pull at all because gravity is taking care of that already. So when I add gravity into play, what would happen is that as I go to this point, I would have less centripetal acceleration because gravity is helping me with the centripetal acceleration. So if I go exactly to the limit where I just want to make this circular motion, nothing more, this object would feel no pull at all at this point. What does it mean it will feel no pull at all? If I put now the direction actually of this, just to make things clearer, the direction of the centripetal acceleration is, this is the magnitude, is outwards. I'm not sure this makes things clear, so I apologize for that, because, okay. What I wanted to say is that the gravity now is taking care of the centripetal acceleration, and at this point exactly, you no longer need centripetal acceleration. So your centripetal acceleration is becoming shorter and shorter and shorter and shorter up to the limit where it is no needed at all, which means that there is no pull in the system. If there is no pull in the system, this object feels no gravity. It feels no gravity, which means that because of the centripetal acceleration now is exactly canceling out the gravity. So A, C minus G equals 0. This would be the acceleration that the object would actually feel. So it would feel as there is no gravity at all, which means if I was inside this system, every time that I would be exactly at the top here, I would feel no gravity. I would float for a fraction of a second. I don't know if this is convincing. It's not, doesn't sound so convincing, because now one can say, okay, you know what? Let's replace the whole thing with something more interesting. If what I say is true, and if I replace it with a bucket of water, so this is a bucket of water, and if I make it go with omega such that the centripetal acceleration is at least equal to the gravity. Why at least? Because if it's less, it means that it will actually fall. It will fail to make the complete run. But if it's equal to the gravity or larger than gravity, then the water there would always be at the back of the bucket and it won't fall down. And this is what I'm going to show you next. And then we're done. Let's make the calculations. So we have a water bucket. Let's take R, this is equal 1 meter. What we want is that the acceleration, now remember the acceleration is v squared over r also, right? The centripetal acceleration to be at least large or equal to g to 10, which means that the velocity should be larger or equal to 3.2 meters per second. Period. Please verify these calculations at home. We take 2 pi r over v. That should be smaller than 2 seconds. Okay, let's try this. Let me just explain here so you can write down this. I have a bucket here, which is about 1 meter. And what we want to do is, as long as I'm able to allow a period of smaller than 2 seconds, then everything should be fine. And if I put water inside here, it will be kept inside and no disaster would be observed. Let me move this now. Okay, so I have the bucket here. I have the water here. Normally, I don't really do it myself. I let one of the students do it. That's the fun part. I have no choice today. Okay. You don't really see the whole thing. Ready for this? Okay. The problem is not really to do it. The problem is to stop it. Okay, you see, no water is coming down. So the centripetal acceleration that I made, if you calculate it, maybe when you see this video again, you would see that it should take less than 2 seconds to make one period, okay? So it follows the calculations that we made. The last thing I will show you, and then I'll release you, is something that I also never really was able to do in the class because of safety issues. Now I think I can do it, but this is what I have. This is a toy sling that I made. It's an office made in the School of Mathematics, and this is what I'm putting for the in the sling. Is an experienced toy there. If you're waiting to see something exciting, I will have to disappoint you. I didn't mention that I have no idea really how to do this. I'm gonna try it now. Okay, so the idea is like this. You make this rotate the way I rotated the bucket, and then at the moment, you have one part of the string is attached to your finger, and at the moment you release the other part, right, in some direction, 45 degrees now, you know, in a 45 degrees, right, and then the object which is inside would now have the velocity vector in that direction, and it would go fly in that direction. It's not gonna happen now. It's probably going to, I don't know which direction, but let's try it. Okay. What? All right. Yeah, that was a failed experiment. So I'll see you next week. Ben, are you there?
Hello, yes.
Okay. Just one thing maybe to add about this, because you can always learn from failed experiments. What we've noticed is that, well, you didn't notice, I noticed actually, this poor guy split into 3 pieces, which I can put back, so no worries. It's used to that. So when we talk about momentum, we would get to something like that, where you have one thing, right, that you put some energy inside it and then result in 3 things that would fly in different directions, but that will come later. Okay, thank you, everyone.
Hello, everybody. You can take 5 minutes for resting, going to the toilet, whatever you need. And I'll start with the tutorial in exactly 5 minutes. Feel free to ask any question. I will be here those 5 minutes. Okay, hello everybody. So first of all, do you have any question around today's lecture, or should I proceed to summarize what Usama saw today? Okay, so basically now we are seeing circular motion, right? Which basically tell us that in the cases that we have seen, we have a rope and some object attached to the end of the rope, and at the other end, we have the center of the motion. And this object is describing some circular path around the center, right? So how we understand this, how we expect this object to keep the trajectory, the circular trajectory, is in a way that we would have some tangential velocity always. So basically, when we work in circular motion, it can be really helpful for us to work in circular coordinates, right? Or to set our reference frame in a way that one of the axes is in the radial direction and the other axis is in the tangential direction. In such a way, we could describe the velocity in terms of its magnitude. But of course, we can always use the reference frame, the standard reference frame, which says that y positive is upwards and x positive is rightwards. So however you prefer. I have seen that some of you have some problems with the notation. So my biggest advice is try to choose the notation that you most like and stick to it always, because there is all the notations are valid as long as you are consistent and you work it out all the time with the same reference frame, right? You can use different reference frames. This is the most used one for 2 dimensions, of course. You can work also with radial coordinates, as I mentioned. In radial coordinates, you would have basically the radial direction and the angle. Those would be the two coordinates that would guide you. Use an angle and a radius, okay? So as we said, we have this velocity, which is the vector that describes this velocity is tangential to the motion. And then we have some, what we call centripetal acceleration, right? Which goes towards the center. We understand that it goes towards the center because otherwise this object wouldn't be able to keep this circular motion, right? If the centripetal acceleration was outwards, this object would just go out of the path, right? I think you will understand this better once we go into Newton's laws of motion and you start understanding how forces act on this object, because as Osama has pointed out perfectly with the example of the water tries to go outwards, right? But we have some force, in this case is the tension of this rope that keeps the ball in this trajectory, right? But that's a bit advanced so far, so we will see that further on. So far we consider the centripetal acceleration inwards, okay, to give some sense to this motion, okay? And as we have seen also, we have the radius of the rope. This centripetal acceleration is function of two variables that we have so far. Okay, so it's function of the velocity, the tangential velocity, and it's function also of the radius. Okay, so it's function of those two variables. Okay, it's important that also you distinguish between linear velocity and angular velocity. Linear acceleration, angular acceleration. Okay, so we have seen that velocity is measured in meters per second, right? A meter is linear, okay? We measure meters on a line. But what about angular velocity? How do we measure angular velocity? Can anyone give me a hint in the chat, or you can talk also, you can unmute your mics? How do you measure angular in angles? Perfect, exactly. So you need angles and you need something else. What else do you need for being a velocity or a speed? Angles and something else. Seconds, angles and time, okay? So our angular velocity is gonna be measured in, for example, radians per second, okay? Let's say radians per second, okay? It can be also measured in degrees per second, but we prefer to work in radians, and I will let you know why a bit later, but it's easier because we can work with pi, and we all know how much is the sine of pi, or we all know how much is the cosine of 2 pi. So it's kind of easier, but feel free to work with degrees. I just recommend you to work with radians, okay? So we're gonna measure angular velocity in radians per second, okay? So the first thing that we need to know, and the most important thing that we need to know in circular motion, is how many radians is a full circle. How many radians is a full circle? It's 360 degrees, and it's 2 pi. Perfect. So how do we measure, how do we calculate angular velocity? We can do 2 pi divided by the time that I take to complete a circle. And what is defined as the time that I take to complete a full circle? Is the period. 2 pi divided by the period. Radians divided by second, okay? Now we have the angular velocity. Okay, that's wonderful. Also, we need to know how to calculate the centripetal acceleration, okay? So far, we are working with uniform motion, okay? We will see later how do we calculate angular acceleration, because we have angular velocity. So if we take the derivative, we can obtain the acceleration. So we can have linear acceleration and also angular acceleration in the same way that we have linear velocity and we have angular velocity, okay? So we also have centripetal acceleration, which is an artifact that we use to give some sense to this circular motion, okay? So in order to have this path, we need some component pulling inwards, okay? So we keep this motion and we don't go away. And this centripetal acceleration is a function of the angular frequency, as which, well, it's function of the velocity and the radius, right? So it's gonna be 2 pi t. I think that's the formulation. Let me check again. Oh no, it's w squared r. Okay. Is that okay? Okay, so we basically know that the angular acceleration is equal to this, the centripetal acceleration. Does this make any sense? Okay. I don't know if you have any question about this type of motion. I also want to show you that some intuition about sines and cosines, right? It's just a small detail that probably you already know, but I just want to make sure that you all know because it's important, okay? So we have this circular motion, okay? And we're gonna fix our reference frame in this way. This is gonna be y positive. This is gonna be x positive, okay? And this is the object with this speed, this velocity, okay, tangential velocity. And then I want to plot the x coordinate with respect to the time, let's say meters, for example. And I want to plot also the y coordinate with respect to the time, okay? So let's say that, for example, here, y is equal to 0. And here, we're going to consider this as the unit ball, okay? The unit ball means that the radius of this circle is equal to 1, okay? 1 meter, yeah? So here, y is equal to 0. Here, y is equal to 1, okay? So basically, if I plot y with respect to the time, I will have a starting 0, okay? Then I go up to 1. Then I go down to 0 again. Here I have y equal to -1. Here I have y equal to 0. I think some of you already know what I'm trying to explain here, right? Does this shape remind you to any function? It's a sine, exactly, it's a sine. So basically, if we take the triangle, right, and this is the angle, you can also plot with respect to the time or with respect to the angle, okay? So because the angle, as Susama mentioned, is function of time, is changing in time, right? Fair enough, it's fine. Okay, the angle changes in time, so it's function of time. So we can plot time or angle. So here we have 0, so this is gonna be x or 1, r is equal to 1, is gonna be r multiplying sine of theta, and this is gonna be theta. Okay, so as you can imagine, x is gonna be related to the cosine. It's gonna start in 1, gonna go down to 0, and go back to 1. Okay, this is very simple, probably you already know it, but it's really important to understand where those charts come from. Okay, how do we explain sines, cosines, trigonometric relations in angular motion, how to decompose vectors. Okay, this is really important. This is the base of everything that you're gonna do. So if you have any question, please feel free to ask anything. You can unmute the mic, talk freely, okay? Wonderful, everybody understands everything. Okay, so now I will proceed to solve the problems that I suggested for the last week. They were just 3. I hope you didn't have any problem. Did anybody have any problem related to them, or were they easy, difficult? How did you feel, guys? All good? Okay, let me see the exercises. Assignment 3. Okay, as you know, I'm uploading the exercises every week around Thursday to the Learning Central. Okay, I hope you already know that. Okay, okay. So I will start by the exercise 3.10. Okay, there is some question. Okay, wonderful, wonderful. Okay, 3.15, the planet X. Okay, that's an interesting exercise, right? So I think we have time to solve all of them. So I'm gonna solve that one. Okay, it was the hardest, but were you able to work it out, guys? I think if you got 3.15, you are very good and you're understanding. You got an answer. Okay, okay. Now I will solve it, so maybe you are able to compare it, and please feel free to ask anything. Stop me anytime, okay? So I will start by a 3.10. Maybe this was the easiest, but it's good to build some confidence before the heart beats. What do you mean with check it effectively? Okay, fair enough, fair enough. Now I will go through the procedure. I believe there is only one way to tackle this problem. So, and I also believe that the most important part of these exercises is the conceptualization. So if your procedure is right, it's very likely that your answer is gonna be right. And I think the procedure is gonna be most of the score. That's how I would do it, okay? So let's just start by the 3.10. Okay. So we have a daring 510N swimmer, dives off. What must her minimum speed be just as she leaves the top of the cliff so that she will miss the ledge? Okay. As I always say, the first thing that you have to do, the most important one, is to sketch the problem. Okay. So we have this ledge, and we have this distance, we have this distance, and we have someone jumping with an purely horizontal speed, V0. Okay. With our 1.75 and 9 and in meters. So if we work here, this in meters, we want to work the speed in meters per second, right? We want to be consistent always. We're gonna also consider, so we can put the reference frame wherever we want, okay? Wherever we want. But in my opinion, the easiest reference frame here would be to say, this is gonna be my X positive, and this is gonna be my Y positive. Okay? Does this make any sense to you guys? You can set the reference frame however you want, okay? But for me, in my opinion, this is the easiest way to set the reference frame. Did anybody set it like this? Oh, you did this. Okay, okay. Smart people, that's amazing. Okay, perfect. So you understand it. You can play with the reference frame to make your life easier. Then we have the equations of motion that are extracted from Newton's laws. We will see that farther on, but so far, let's stick to the displacement equation. For example, we know that displacement in, like, let's say the final x, xf, is gonna equal to some initial x plus some initial velocity in x. Okay, this is in x direction. V0 is equal to V0x plus V0y. But in this case, we know that this is 0. Multiplying some time plus some half of the acceleration in the x direction times square. YF is the same, right? With YT plus 1/2 AY T squared. We know that the T is shared, okay? They are the same, okay? So what are we asked? What is the initial speed that she needs to have? Which is, okay. So if we try to tackle this equation, we will realize that we have two unknowns and only one equation. So we cannot solve it. However, here we have everything except t. So we have one equation, one unknown. So from this equation, we know that YF is 9, okay, 9 meters is equal to 0 meters plus initial speed in the y direction. We know is 0, 0 multiplying t plus 1/2. We know that the acceleration in the y direction is equal to the gravity, okay, g, 9.81 seconds squared. So we need time squared. So from here we can just say that, okay, we cancel this, we cancel this. So we just have this and this, and we have that 18 meters divided by 9, okay, 0.81, something like that, right? Oh, you can't see what I'm writing. Oh, fair enough. Sorry. I'm really sorry. Up to where can you see? Can you see now what I? Okay, wonderful, wonderful. Sorry. I apologize for that, guys. My bad. Okay, seconds. Okay, does this make sense? So basically, we have two equations, one for the displacement in x, one for the displacement in y. So we start working out the y because we know everything except the time. So we want to figure out the time. We know the acceleration, the initial speed, everything. Now we have the time, okay, and we go back to the x displacement in the x direction. Okay, so we know that the final x is equal to, let's say, 1.8 to overcome it, or 1.75, whatever you want. So she wants to overcome this 175. So I'm gonna write 1.8, okay? But if you write 175, I think it's also valid, okay? It's just like a small detail. X0 is equal to 0. V0, this is what we want to calculate. Now we know t. We know t from the y equation, okay? 18, not 12. 18, not 12. Oh, yeah, because it multiplies. Sorry. Yeah, definitely. I don't know why I wrote 12. It's 2 multiplying 9 is 18 meters and divided by 9.81 and the square root of that. Wonderful, guys. You have a very good eye, yeah? Spotting mistakes. That's perfect. Okay, is that right now? And once you have t, you plug it in here and you just obtain V0x, okay? So basically that's how you have to tackle this problem. Yeah. Okay, wonderful. So basically you just plug t here and here. No, here not, because you don't have acceleration in x. So this goes. So basically you have that V0x is equal to 1.8 meters divided by whatever t you calculated here, okay? That's your solution. Okay, let's go through to the next problem. Okay. Exactly. That's what I say. So basically, we don't have acceleration in the x direction. That's why our final displacement is equal only and only to the velocity multiplying the time. We don't have initial position. We don't have x acceleration. So that's completely right. We only have acceleration in the y direction because we have the force of gravity. Okay, very good, smart people. Yes, exactly. We take 1.8 to prove that she gets over. I'm not gonna write the exam, I'm not gonna mark it. But I think if you write 1.75 should be fine, as long as you demonstrate that you understand the rest of the problem and you understand the procedure that you have to take, okay? But you definitely can write 1.75. I think it's really important that everything that you do in the exam, you justify it, okay? So you have, feel free to write anything in the exam because Susama is a reasonable person. So in case you use 175, write, okay, I consider that with 1.75, she is overcoming the ledge. If you write 1.8, you can justify it. Try to justify as much as you can, okay? It's really important. In science in general, you have to justify everything that you do. 3.15, okay. Our beloved problem. Inside a starship at rest on the Earth, a ball rolls off the top of a horizontal table and lands at a distance d from the foot of the table. Okay, sketch. So this is gonna be my table, okay, more or less. And we have a ball, okay, that rolls off the table. So I consider that the ball only has initial speed in the x direction. So I'm gonna consider that it only has initial speed in the x direction. I consider that there is some gravity that I'm gonna call G or G1 or G. And I'm gonna consider that the table has a height of h, okay? And it lands at a distance d. So basically we know that the ball is gonna do something like this, okay? This is the floor, and it's gonna land at a distance d, okay? This is the case, the first case. Then the commander, captain, rolls the same ball off the same table with the same initial speed as on Earth, and it finds that it lands at a distance 2.76 d. So now the captain rolls ball off the same table, okay? We know it's the same table, so it's gonna have the same height. Have the ball, same initial speed, which I consider is only in the x direction. There is not initial speed in the y direction. Okay, and now it lands at 2.76 d. Okay, but now we have a different gravity. Okay, we're gonna call it G2. So the first thing, this is a very intuitive problem. You have to use your intuition here, okay, guys? What's the acceleration? Okay, this acceleration is gonna be G2. We have to calculate G2. First of all, when I look at the sketch, the first thing that I can say about G2 is that I think it's gonna be smaller than G. Okay, why do I reach this conclusion? Okay, so if both have the same velocity in the x direction, but the second one reaches way farther, means that is with the same speed, means that it's gonna take more time to reach the floor, okay? If it takes more time to reach the floor, it means that this gravity is smaller than this one. It's pulling with less force, okay? That's why this ball is taking longer, okay? So that's the first thing I can say about this, okay? So the first thing that I can also do is to try to work out equations, okay? So what I think I can do is I'm gonna try to relate the x displacement for the case 1 with the x displacement for the case 2. Okay, so v, okay, the x displacement d is gonna be equal to initial position in both is 0, okay? 0 plus V0x multiplying T1. T1 is gonna be the time that this ball takes to reach the floor, okay? But we don't have acceleration in the x direction, okay? So this is the equation for the x displacement of the first case. In the second one, we have that 2.76 d is gonna be equal to the same speed, v0x, but now the time is gonna be different. We have just mentioned that this ball is gonna take longer than this one to reach the floor. We know that they are not gonna take the same, even though we don't know that it's smaller the time or shorter. We know that it's not the same. They are not gonna reach the floor at the same time because they have the same speed and one is taking a longer path, okay? So we call it T2, okay? So maybe now we can establish some relations between the times that they take, okay? What we can do is, okay, this equal to V0 T1. So I'm gonna try to substitute this D in here to see what is the relation between T1 and T2. I want to see which one is bigger, okay? So I substitute, take 2.76 multiplying V0x T1 V0x T2, okay? Oh, look, they are the same speed. They cancel out. So T2 is gonna be equal to 2.76 times T1. Okay, do we understand until here what I'm doing? Does it make sense what I've done? Wonderful. So basically, I know that one is taking a longer path, and I want to make some conclusions about what is the relation between the times that they take. So basically, I equalize the x displacement equations. So now I know that T2 is 2.76 times longer than T1. Now I'm gonna try to see what happens if I relate the y displacement equations, because I know that both of them, the final y is the same, is h, or whatever you call it, h, a y final, you can call it however you prefer, but you know they are the same because it's the same table. It says in the problem it's the same table, okay? So I'm gonna just skip this, T2 equal to 2.76T1, and I'm gonna erase that, okay? Just to make a little bit of more space. This is important, keep it in mind. So now I'm gonna try to relate the y displacement, okay? So I know that for the first scenario case, h, okay, again, my reference frame is gonna be x positive, y positive, okay? I'm gonna use the same reference frame as in the previous exercise. So h, which is positive because my reference frame says that downwards is positive, my final displacement, h, is gonna be equal to my initial position, 0, this is the 0, plus initial speed in y is 0, the initial speed in the y direction, okay? We only have initial speed in the x direction. So we just have acceleration, 1/2 g t squared, t1, okay? Because it's the first scenario. The second scenario, we realize that we have again the same reference frame, x positive, y positive, same final y displacement, which is h, but we have different gravity. We don't have y initial position, we don't have initial velocity in the y direction, so we just have acceleration, which is g2. g2 t2 squared, okay? Both are equal to h, so I can just equalize them. I will just equalize them, right? So I can get rid of h, which I don't know. So 1/2 gt1 squared is equal to 1/2 g2 t2 squared, okay? So what do I have here? Well, I have one equation, okay, with, well, let's suppose I know g, which is 9.81. So I have 1, 2, 3 unknowns, okay? I cannot solve this so far. So what am I gonna do? I'm gonna plug this in here, okay? The relation between the times. So I'm gonna plug it into 2. So I'm gonna do 1/2 g t1 squared is equal to 1/2 g2. Well, this 1/2, we can get rid of it, right? To make things simple. T2 is equal to 2.76 T1 squared, okay? Does this make sense that I square both? Okay, it would be this. But we know that this is equal to 2.76 squared multiplying T1 squared, right? So I can cancel T1. Do you see, guys? What's happening? Yes, wonderful. So what do I have? I have that G is equal to G2 2.76 squared. I have a relation. I have one unknown, one equation. I know G, so I can just say that G2 is equal to G 2.76 squared. This is my solution. Okay. So do you understand what I've done? So basically what the steps that I have taken to understand how to reach the solution, okay, was first of all, sketch, essential. You need to have a sketch, okay? After you have the sketch, my suggestion is that you write your tools here. What are my tools? The displacement equations, okay, are my tools here. Once I write the sketch, I have my tools, I can start working out the exercise. I can say, okay, I'm gonna use this, I'm gonna try this. You can start trying things, but first you have to have your tools ready and your sketch ready, okay? And I think it's already a time. If do you want me to solve the last exercise very fast, or do you want to stop here, guys? It's completely up to you. If you want to leave, you're free to leave. Or does anyone want to see the last exercise? Or okay, yes, sure. I will do it really fast. Okay, guys. So I will just sketch the last exercise so at least you know how it's done. But I think this one was the most complicated today. I'm sorry if I took too long to solve it, but I really wanted to make sure you understand. A man stands on the roof of a 15-meter tall building, throws rock. Okay, I have some small solutions. Here, 3.21, okay, that I wrote the day. So I have this building, I know the height of the building, which is 15 meters. I know the initial speed and the angle, 33 degrees, the initial speed, V0. Okay, the first thing I need to know is that, give me a second. So the first thing you need to know is that V0, to decompose V0, okay? So I have V0, I have the angle, 33 degrees. So this is V0x, V0y. V0x is equal to V0 cosine 33 degrees. V0y is equal to V0 sine 33 degrees. Okay, so you can calculate both. That's important to know. What am I asked? So the maximum height at the roof. Okay, so basically you know that this is going to be the trajectory. At the top of the trajectory, the y speed is equal to 0. So at this point, Vy is equal to 0. Okay, why? Because we have g. Okay, so we know that V0y, Vy minus V0y are going to be related to this change is going to be produced by the gravity. Okay, so the final speed, what Vy, which, Vy, which is equal to 0, because at the top, so the speed, the y speed, goes decreasing, here is 0, and goes increasing downwards. So it changes sign. 0 is equal to some initial speed, V0y, that we know here, okay, plus the acceleration in y multiplying the time, okay? We know that acceleration multiplying time give us speed. We know the acceleration, which is g, so we know that 0 is equal to V0y, which is here, V0y, plus the acceleration, which is minus 9.81 multiplying t. So I obtained the time that it takes to reach this point. And now I can apply the y displacement equation. Okay, so I know that this h is going to be equal to the initial position is 0, the speed multiplying the time, V0y multiplying time, okay, plus 1/2 of the acceleration minus 9.81. The sign is really important. The gravity is pulling downwards. The acceleration, ag or g, are downwards. And my reference plane now is y positive, x positive. So my g is negative, t squared. So now I can calculate h, okay? What else? Well, I think now you can just calculate most things, okay, guys? I think we really run out of time, so I will send you the solutions, guys, okay? I'm sorry that we completely run out of time. I will send you the solutions by tomorrow's night, okay? So keep a look on Learning Central, guys, and feel free to mail me or send me anything. How do you pronounce that? Is diolch? Can you unmute your mic and teach me how to pronounce that? Oh, don't worry. Is diolch? Is it diolch? Okay, diolch everybody, guys, and see you soon. Have a nice day.